Welcome to this video for forced harmonic motion, and we're going to start again by looking at the GeoGebra app that is linked from ActiveLearn. So I've set this up first of all so that you can see that this is damped harmonic motion that we saw before, and this is light damping. We can tell that it's light damping because it goes back down below the axis. So if I start this off, let's just go t equals 0, start it off. There's our particle. The displacement is being modeled on the vertical axis either side of a central point. So we're going to pause that now. If I reduce, this k is the coefficient of dx by dt. If I reduce that down to 0, then we just get our simple harmonic motion. So let's leave it at 0.4 for the moment. Now, our differential equation here, we can see its discriminant, it's negative. We can also see that on the right-hand side, we've got something more complicated than we had before. I've set both of these coefficients to 0, but what we have is a differential equation, which if we change these coefficients, will no longer be a homogeneous one. Coefficients of sine of t and cos of t are p and q. So let's just have a look and see what happens if I change one of these. So I'm going to say, so remember that we're still leaving this discriminant as negative. So our homogeneous equation, or the left-hand side of this, there's no changes to the solutions to that. So if I change p to something like this, you can see that there's a change, so that if we've got 4 sine t over here, eventually, after the damping goes down to damp the motion down very small, we're still left with something where x is, it's now turning into simple harmonic motion. And what's happening here is that the function on the right-hand side here is kind of taking over, if you like. That's it's forcing the motion into the motion that its function models. If we put in q as well, that's really just a combination of the two trig functions, and we can work out what the amplitude is going to be from the r that we would get if we turn this into r cos theta plus alpha. So it's just going to be 4 squared, square root of 4 squared plus 1.7 squared. Let's just bring that back down a bit. You can see that when we have forced harmonic motion, we get some quite strange things happening. So, for example, here we go up to this peak, but then we come down to something where we might expect a drop down there, but it doesn't happen because the two functions are really superimposed upon each other. So yeah, we can get some what look like slightly odd things going on. So particular down here, we're going to go down up to 0, but then back out again. Without solving our differential equation, it's it looks like quite unpredictable motion, which then does settle down eventually into motion that is much more predictable. So when we have a differential equation which models damped harmonic motion, if it is a homogeneous equation, so it equals 0, but it's not a homogeneous equation, we've got a trig function, or we've got some function on the right-hand side, that is called a forced harmonic motion. So let's have a look at an example now of forced harmonic motion and work through this one. So in the course workbook, we've got this example similar to the one that we saw for, or one of the ones that we saw for damped harmonic motion. We've got a particle moving along the x-axis. We're modeling its displacement using the variable x, and then we've got speed and acceleration, and we've got some forces acting on that particle. So let's have a look at the diagram for this this example. So I'll just try and keep that example there for you. Here's our particle P. Here's the displacement x from the origin O. We're taking positive this direction, so velocity positive this direction, acceleration positive this direction. It says three forces act on P. A restoring force of magnitude 7.5 x newtons. Restoring force means that it's trying to restore P to the center of the towards the origin. So it's always going to act towards the origin. So I'm going to put that in like this. There's my force of 7.5x. We've got a resistance to motion of 6v. Well, we're taking motion velocity to be that way, so our 6v is going to act this way, so that's acting that way as well, 6v. And we've got a force of magnitude 12 sine t acting in the direction of OP. Well, OP is that direction, so we've got 12 sine t acting in that direction. 12 sine. Did it say 12 sine t? Yeah, 12 sine t. There we are. So just as we did before when we looked at the damped harmonic motion example, we're going to take the sum of the forces is equal to mass times acceleration. So in this case, what are the sum of the forces? Well, this one's negative, this one's negative, this one's positive. So we've got why is that one negative? We should have 12 sine t acting in the direction of OP. Okay, so 12 sine t minus 7.5x minus 6v is equal to, what was the mass? The mass was 1.5a. So if we rearrange these over here, we've got 1.5a plus 6v plus 7.5x is equal to 12 sine t. Oops. We need to divide through by 1.5, and we've now got, and let's write a as d2x by dt squared, v as dx by dt, and yeah, actually let's do that first. So 1.5 d2x by dt squared plus 6 dx by dt plus 7.5x is equal to 12 sine t. Divide through by 1.5 and we get d2x by dt squared plus 4 dx by dt plus 5x is equal to 8 sine t, and that is indeed the differential equation that we're asked to show. So now it says, part B says find x as a function of t, so we're going to solve this equation. So for B, we're going to start by solving the homogeneous equation. So the auxiliary equation is m squared plus 4m plus 5 is equal to 0. So m plus 2 squared plus 1 is equal to 0. So m is equal to minus 2 plus or minus I. So the complementary function is x is equal to e to the minus 2t times a cos t plus b sine t. Right, we now need a particular integral for our function. So the particular integral is going to be in this form, x is equal to c sine t plus d cos t. So if we differentiate that, x dot is equal to c cos t minus d sine t. X double dot is going to be minus c sine t minus d cos t. So we're going to put those back into our equation. So we need x double dot, which is minus c sine t minus d cos t, plus 4 times x dot, so plus 4c cos t minus 4d sine t, plus 5 times x, so that's plus 5c sine t plus 5d cos t is equal to the right hand side, which is 8 sine t. So we've now got, comparing coefficients of sine and cosine. So sine, we've got minus c minus 4d plus 5c is equal to 8. Let's rewrite that as 4c minus 4d equals 8, or c minus d equals 2. And cosine, let's do that over here. We've got minus d plus 4c. What's I doing? Cosine plus 5d equals 0. So that's 4d minus 4c equals 0. D minus c equals 0. If we add these two together, we're going to get no, wait a minute, that can't be right. It's plus there. There we go. D plus c. If we add these together, we're going to get 2c is equal to 2, so c equals 1, and d equals minus 1. C equals 1, d equals minus 1. So the particular integral is, what did we have? X equals, C was 1, so sine t minus cos t. So let's write out our general solution now. Our general solution is x is equal to e the minus 2t a cos t plus b sine t plus sine t minus cos t. Okay, so now we're going to use the initial conditions that we've got. When t equals 0, x is 5, and its velocity dx by dt is 2. So let's do that now. T equals 0, x equals 5. So we've got 5 is equal to, this is 1, this is 1, so we're going to have a, this is 0, this is 0, this is 1, so a minus 1, so a is equal to 6. T is equal to, we need to differentiate, don't we? So we've got x dot is equal to, well, if we differentiate this, we're going to get minus 2e to the minus 2t times a cos t plus b sine t plus, so we're using the product rule here. This is just half of my product rule, e to the minus 2t. Then we're going to differentiate what's in the bracket. So that's going to be minus a sine t plus b cos t. And then we've also got to differentiate these. So we're going to say that that's plus cos t plus sine t. Is that right? Yeah. T equals 0, x dot equals 2. So 2 is equal to, substitute in here, well, we've got t equals 0, so this is going to be minus 2 times a plus 0, so that's a, plus, it's going to be 1 times b, so that's just b from here. Substitute in t equals 0, we get 1 there and 0 there, so plus 1. Now, what do we know? We know that a is 6, so this is 2 is equal to minus 12 plus b plus 1. Take away the 1, add the 12, and we get b is equal to 13. So our final particular solution to the differential equation is this: x is equal to e the minus 2t times, what did we have? A equals 6, so 6 cos t plus 13 sine t plus sine t minus cos t. And then the next part of the question says describe the motion when t is equal to large. So even if you can't remember exactly what this is called, you can think what happens when t gets large here. So we can say as t tends to infinity, e to the minus 2t, so this term here is going to tend to 0. So this whole term will tend to 0, and x is going to, we're going to say so x tends to sine t minus cos t. We can write that as for large t, x is approximately equal to sine t minus cos t, which is root 2 sine of t minus pi over 4. We could write it in terms of cosine, root 2 cos of, I think it's t plus pi over 4, but I may have got that slightly wrong. The important point is that root 2 is going to be the same. So which is simple harmonic motion with period 2 pi or 6.28 seconds and amplitude root 2 or 1.4 meters. Okay, thanks for bearing with me through this long example. I hope it was useful. That's it for damped and forced harmonic motion, which is covered in the textbook, in the examples, and the examples before exercise C, and then exercise C. You'll find that exercise C, the first 5 questions, I think it is, are on damped harmonic motion, and then there are 3 questions on forced harmonic motion. Thanks for watching.